Picture the night sky, its vast tapestry of stars, each one a distant sun glowing across the unimaginable stretches of space. Now imagine one of those stars suddenly winking out, as if something colossal passed in front of it, blotting it from view. Not a planet, not an asteroid, something far stranger, something artificial. What if that star didn't vanish naturally? What if its light was blocked by a structure so enormous, so advanced, that it defies everything we know about engineering? This isn't science fiction. It's a real possibility astronomers are searching for right now, and it could be our first glimpse of an alien civilization's handiwork. The idea of alien megastructures, artificial constructs designed to harness or even obscure the light of stars, has fascinated scientists and dreamers alike for decades. These wouldn't just be buildings or machines, they'd be cosmic-scale marvels, feats of engineering so vast they could reshape entire solar systems. One of the most intriguing candidates. A Dyson sphere, a theoretical shell built around a star to capture its energy. But there are darker possibilities, two structures meant to conceal, to redirect, or even to signal. What if some of the strange dimming patterns we've observed in distant stars aren't natural at all? What if they're evidence of something or someone out there building on a scale we can barely comprehend? That's the mystery we're diving into today. From unexplained stellar flickers to the mind-bending physics of how such megastructures could even work, we'll explore the cutting-edge science behind these cosmic enigmas. Could they be the key to finding intelligent life beyond Earth, or are they just cosmic oddities, tricks of light and dust? The answers might rewrite our place in the universe. So let's embark on this journey together, peering into the depths of space to uncover what could be hiding in the darkness. Structures so immense, so alien, they might just be blocking the light of stars themselves. Alien megastructures are exactly what they sound like: colossal artificial constructions, engineered on a scale so vast they could dwarf planets or even entire star systems. These aren't just bigger versions of what we build on Earth. They represent an entirely different tier of technology, one that manipulates the very fabric of a solar system. Take the Dyson sphere, for example, a concept first proposed by physicist Freeman Dyson in the 1960s. Imagine wrapping a star in a massive shell of solar panels, capturing nearly all of its energy output. For a civilization that's exhausted the resources of its home planet, this would be the ultimate power source, turning a sun into a cosmic battery capable of fueling unimaginable advancements. But energy harvesting isn't the only reason an advanced civilization might build something so enormous. Picture a Shkadov thruster, a theoretical megastructure that works like a stellar engine, using a giant mirror to reflect a star's own light and slowly push it through space. Why? Because if you could move a star, you could effectively steer an entire solar system, navigating the galaxy over millions of years. It sounds like something out of a far future sci-fi novel, but the physics checks out. A civilization capable of engineering on this scale wouldn't just be surviving, they'd be reshaping the cosmos to suit their needs. Then there's the darker side of megastructures. What if some aren't built to harness light but to block it? A cloaking sphere, for instance, could be designed to hide a star entirely, making it invisible to outside observers. Whether for defense, secrecy, or something beyond our comprehension, the possibilities are as unsettling as they are fascinating. And here's the most compelling part: astronomers have already spotted stars that dim in strange, irregular ways, as if something massive and unnatural is passing in front of them. Could these be the fingerprints of alien megastructures, or are they just cosmic oddities we haven't fully explained yet? The search for answers is already underway, and what we find might change everything we know about our place in the universe. Here's where things get even more intriguing. Alien megastructures might hold the key to one of astronomy's greatest mysteries, the Fermi Paradox. Named after physicist Enrico Fermi, It's the puzzling contradiction between the high probability of alien civilizations existing in our vast universe and the complete lack of evidence for them. If the cosmos is teeming with life, why haven't we seen even a single trace? Megastructures could offer an answer. Imagine a civilization so advanced it doesn't just inhabit planets, it reshapes entire stars. Such a culture might not broadcast radio signals or send out probes. Instead, it could be silently harvesting energy, moving stars, or even hiding itself deliberately. Think about how humanity's own energy consumption has evolved. 1,000 years ago, we relied on fires and windmills. Today, we're tapping into solar panels and nuclear reactors. Now project that forward another million years. A civilization at that stage might see planets as quaint relics, opting instead to build planet-sized power grids around stars. They wouldn't need to colonize the galaxy. They'd have all the energy they'd ever require right at home. That could explain why we don't see them. They're not traveling between stars. They're too busy engineering them. But there's a darker interpretation. What if advanced civilizations eventually turn inward, constructing vast cloaking megastructures to shield themselves from potential threats? In a universe where survival might depend on staying hidden, the most intelligent move could be silence. It's a chilling thought that the reason we don't detect alien signals isn't because they aren't out there, but because they're deliberately avoiding us. Or perhaps we're simply looking in the wrong way. Traditional searches for extraterrestrial intelligence focus on radio waves, but a civilization building Dyson Spheres or star-shrouding megastructures might communicate or exist in ways we haven't even considered. Their technology could be so advanced it's indistinguishable from natural phenomena. That flickering star we dismissed as an oddity, it might not be a cosmic coincidence. It could be a sign we're not alone after all. Among the most staggering concepts in theoretical megastructures, the Dyson Sphere stands out as both a monument to engineering ambition and a potential signature of advanced alien technology. Picture millions or even billions of solar collectors arranged in a vast swarm around a star, each one absorbing a fraction of its radiant energy, rather than a single solid shell, which would face near impossible structural stresses. Most modern iterations propose a dynamic network of orbiting habitats, power stations, and reflective panels. Together, they'd form a loose but coordinated web, intercepting enough sunlight to meet the energy demands of a civilization that has long outgrown the limits of planetary resources. From our vantage point, such a structure would create an unmistakable fingerprint. A star wrapped in a Dyson swarm wouldn't vanish completely, but its light would flicker unevenly as the collectors passed in front of it, dimming in unpredictable patterns. Some wavelengths might be absorbed entirely, while others leak through gaps in the swarm. This isn't just speculation. Astronomers have already catalogued stars that exhibit exactly these kinds of anomalies. Take KIC 8462852, nicknamed Tabby star, after the scientist who first noted its bizarre behavior. It dims by up to 20% at irregular intervals, far more than any known planet could explain. Dust clouds or cometary debris might account for some of it, but the sheer scale of the dimming leaves room for more exotic possibilities. The energy potential of a Dyson sphere is almost incomprehensible. Our Sun emits roughly 380 sextillion watts every second, a number so large it's meaningless without context. But to a civilization that's mastered interstellar engineering, that energy could fuel quantum computers the size of moons, interstellar arcs, or even experiments in bending spacetime itself. This isn't just about powering cities, it's about unlocking capabilities that border on magic by today's standards. Yet the real wonder lies in the unintended consequences of such a project. A Dyson swarm would radiate waste heat infrared signatures detectable across the galaxy. In fact, some researchers have scanned the skies for exactly this, searching for stars that glow unusually bright in infrared despite appearing dim in visible light. A few candidates have emerged, though natural phenomena like dust rings can mimic the effect. Still, the hunt continues because finding even one confirmed Dyson structure would answer humanity's oldest question: are we alone? But here's the twist: what if we're looking at Dyson spheres all wrong? Maybe they're not just power plants. A sufficiently advanced civilization might use them as cosmic mirrors, redirecting starlight to propel ships or even terraform distant worlds. Or perhaps their computational infrastructure, with each panel acting as a node in a stellar-scale supercomputer. The more we unravel the possibilities, the clearer it becomes. If these megastructures exist, they're not just evidence of alien life. They're blueprints for a future where humanity, too, might one day reach for the stars. A full-fledged Dyson sphere may be the ultimate energy megastructure, but not every advanced civilization would need, or even want, to enclose their star completely. That's where partial Dyson swarms come into play. Imagine a stellar power grid built in stages, with vast clusters of energy collectors positioned in careful orbits around a star, capturing sunlight without fully surrounding it. These wouldn't be uniform rings or symmetrical patterns. They'd be sprawling, dynamic constellations of mirrors, solar panels, and habitats drifting in deliberate formations. Unlike a solid shell which would block all light, partial swarms would let starlight slip through the gaps, creating a flickering effect like sunlight filtering through the leaves of a cosmic-scale tree. This patchwork approach solves some of the biggest engineering hurdles of a full Dyson sphere. For one, it eliminates the need for impossibly strong materials to withstand a star's gravity and radiation. Instead of a single brittle shell, a swarm could be built incrementally, with individual components adjusted or replaced over time. It's the difference between constructing a glass dome over an entire city and launching a fleet of floating solar platforms. One is theoretical, the other already within our near-future capabilities. The real clue to spotting these partial swarms lies in their light signatures. A natural phenomenon, like a planet passing in front of its star, creates a predictable, rhythmic dimming. But a partial Dyson swarm would dim the star irregularly, with dips in brightness that vary in depth, duration, and timing. Telescopes like Kepler and TESS are designed to detect exoplanets by spotting these precise, repeating shadows. When they find a star that dims in chaotic, asymmetrical ways, no clear pattern, no planetary explanation, that's when astronomers start asking harder questions. Take Boyajian's star again. Its dimming events aren't just deep, they're erratic. Some dips last for days, others vanish in hours. At times, the star's light drops by 20%, then rebounds unevenly, as if something with complex geometry is passing in front of it. A dense comet swarm could explain some of this, but comets don't account for the long-term, gradual dimming the star has exhibited over the past century. A partial Dyson swarm, though, that fits, but there's another possibility, one even more intriguing. What if these swarms aren't just static energy collectors? Advanced civilizations might use them as adjustable mirrors, tilting panels to beam concentrated light toward interstellar probes or distant colonies. Think of it as cosmic infrastructure, a network of orbital mirrors that can redirect sunlight on demand, turning a star into a navigational lighthouse or a power source for far-flung expeditions. The implications are staggering. If we ever confirm the existence of a partial Dyson swarm, it wouldn't just mean we've found aliens. It would mean we've glimpsed a civilization thinking on timescales and scales we can barely grasp. These wouldn't be relics of some long-dead empire. They'd be proof of a culture actively reshaping its solar system, not for the next election cycle or even the next century, but for the next million years. And if humanity ever reaches that level of mastery over energy, the universe might just become a little less dark and a lot more mysterious. If a Dyson sphere represents the ultimate power grid, then a Shkadov Thruster is the universe's most ambitious engine, a megastructure designed not just to harness a star's energy but to move the star itself. Picture a colossal mirror spanning millions of kilometers, positioned just close enough to a star to catch its radiation pressure. Unlike a Dyson swarm, which surrounds a star to collect energy, this mirror would act like a solar sail on a cosmic scale. Photons streaming from the star would push against it, and because the mirror isn't perfectly balanced, that push would nudge the entire star slowly, imperceptibly, but irrevocably in the opposite direction. This isn't just theoretical. The physics behind the Shkadov Thrusters is surprisingly straightforward. Stars emit light in all directions, creating a natural outward pressure. Normally, that pressure is symmetrical, cancelling itself out. But place a giant mirror on one side, and suddenly, the escaping photons hitting the mirror get redirected backward, imparting momentum. The star, in turn, recoils like a rocket expelling exhaust, except here, the exhaust is starlight itself. Over millions of years, even this gentle push could accelerate a star to noticeable velocities, steering it and its entire planetary system across the galaxy. The observational signatures of such a structure would be bizarre and unmistakable. A Shkadov mirror wouldn't block all of a star's light, just enough to create an asymmetry. From our vantage point, the star might appear to wobble erratically, its brightness fluctuating as the mirror's angle shifts relative to Earth. Unlike the predictable dimming of a planet transit or the erratic flickers of a Dyson swarm, this wobble would follow a peculiar pattern. The star's light might dip slightly more on one side, as if it's being tugged unevenly. Some wavelengths could dim more than others depending on how the mirror reflects them. And here's where it gets even more fascinating. A civilization capable of building a Shkadov thruster wouldn't just be altering their star's position, they'd be rewriting their cosmic neighborhood's future. Moving a star means moving every planet, asteroid, and comet orbiting it. Imagine relocating an entire solar system to avoid an impending supernova, or navigating closer to resource-rich nebulae. It's the ultimate form of terraforming, not just reshaping a world, but repositioning the sun that lights it. Yet the most chilling possibility isn't about where these stars are going, it's where they've already gone. If advanced civilizations have been using Shkadov thrusters for millions of years, some stars in our galaxy might not be where natural physics placed them. Their positions, their velocities, even their trajectories could carry the fingerprints of intelligence. Astronomers have already catalogued stars moving unusually fast or in odd directions. Most have natural explanations, but what if some don't? The evidence might be hiding in plain sight, waiting for us to recognize the unnatural drift of a star that wasn't meant to wander. And that raises a profound question. If we ever found such a star, how would we know its movement was artificial? The answer lies in the details, the subtle anomalies in its light, the way its velocity defies local gravitational fields, or the infrared glow of a mirror too vast to be natural. Detecting a Shkadov thruster wouldn't just prove we're not alone. It would reveal a civilization thinking in epochs, engineering on scales that make our greatest projects look like sandcastles. For them, stars aren't just points of light, they're engines, and the galaxy is a highway. The real mystery isn't whether such beings could exist, it's whether we're already seeing their work and just don't realize it yet. While the Shkadov thruster pushes stars with sunlight, the Kepler thruster takes stellar engineering to an even more astonishing level, harnessing the star's own nuclear furnace for propulsion. Named after astrophysicist Matthew Kepler, this theoretical megastructure works like a cosmic tugboat, combining elements of a Dyson swarm with particle accelerators on an unimaginable scale. Here's how it would work. An array of enormous electromagnetic fields would siphon material from the star's surface, funneling hydrogen and helium into a series of particle accelerators orbiting nearby. These accelerators would compress the stellar material until it ignites in controlled fusion explosions, channeling the resulting energy into focused jets shooting out from the star's poles. One jet propels the star forward like a rocket exhaust, while a second, more powerful jet fired in the opposite direction stabilizes the entire system, preventing the star from tumbling out of control. Unlike the gradual drift of a Shkadov thruster, a Kepler thruster could move a star across interstellar space in mere millions of years, a blink of an eye by cosmic standards. The sheer scale of this engineering is hard to overstate. The particle beams alone would stretch for billions of kilometers, visible across galaxies as twin lances of plasma brighter than some nebulae. And just like any megastructure, this one would leave shadows. The orbital arrays collecting stellar material would intermittently block portions of the star's light, creating irregular dimming patterns distinct from anything natural. But the real smoking gun, the jets themselves, as they pulse with controlled eruptions, they'd emit bursts of high-energy radiation X-rays and gamma rays that telescopes could detect as unnatural spikes in the star's emission spectrum. Then there's the infrared signature. Any civilization capable of building a Kepler thruster would inevitably waste some heat, glowing faintly in wavelengths our telescopes can already scan. In fact, there's a known star that fits this profile, KIC 734547. It dims unpredictably, emits occasional high-energy flares, and has an infrared excess that doesn't match any known natural phenomenon. Could it be a stellar engine mid-construction, or just another cosmic oddity? The line between astrophysics and potential alien technology has never been thinner. But why would a civilization go to such extremes to move a star? Survival might be the simplest answer. Picture a rogue black hole entering the outer reaches of a solar system, its gravity threatening to fling planets into chaos. A Kepler thruster could nudge the star, and by extension, its inhabited worlds out of harm's way. Or consider long-term cosmic planning, relocating to richer galactic neighborhoods before interstellar gas clouds deplete, or positioning a star near a future galactic merger to harvest new resources. This isn't just about avoiding catastrophe, it's about proactive cosmic stewardship. Yet the most fascinating aspect might be what these engines imply about their builders. A species that masters stellar propulsion isn't just surviving, they're orchestrating the movement of celestial bodies like pieces on a chessboard. Their projects unfold across eons, their engineering visible not in city skylines but in the trajectories of stars. If we ever confirm a Kepler thruster's existence, it won't just reveal aliens. It'll reveal architects of the galaxy, beings who don't just live under the stars, they command them. And that realization might change how we see every unusual twinkle in the night sky. Black holes aren't just cosmic vacuum cleaners, they're powerhouses of gravity and energy, and for a civilization advanced enough to harness them, they could be the ultimate foundations for megastructures. Imagine an engineering project so vast it wraps around the event horizon itself, tapping into the swirling maelstrom of an accretion disk or even riding the gravitational waves like a surfer on spacetime's edge. The energy output here dwarfs anything a star could provide. A single black hole's accretion disk can shine brighter than entire galaxies, its matter heated to millions of degrees as it spirals toward oblivion. Now picture an array of colossal mirrors or energy collectors positioned just outside the point of no return, skimming plasma from the disk like a cosmic siphon. This wouldn't just be a power source, it would be a forge for technologies operating at the extremes of physics. But black holes offer more than raw energy. Their gravity is so intense it bends light into loops, creating natural lenses that could focus radiation or even serve as interstellar communication relays. A photon sail positioned in the warped space around a black hole could catch not just starlight, but beams of energy bent full circle by gravity, amplifying their power exponentially. And here's where it gets eerie. From a distance, some of these megastructures might look indistinguishable from natural phenomena. A black hole with an artificial accretion disk tap might flicker unpredictably, its light dimming and flaring as collectors intercept streams of hot gas. To an outside observer, it could resemble a rare quasar or a black hole feeding on a passing star unless you knew what to look for. Then there's the concept of a black hole cloak, a megastructure designed not to harness energy but to manipulate perception. By strategically redirecting light around the event horizon, a sufficiently advanced civilization could make a black hole appear smaller, larger, or even invisible to distant telescopes. Think of it as cosmic camouflage, turning the most destructive force in the universe into a hidden stronghold. The signals would be subtle, perhaps an absence of lensing effects where gravity insists there should be one, or thermal emissions that don't match theoretical models. The real challenge in detecting such structures lies in their sheer scale and the violence of their environment. A black hole's accretion disk is a storm of radiation and magnetic forces that would vaporize any known material. But a civilization that's mastered atomic scale engineering or force fields might see it as just another resource. They could build collectors from hyperdense matter stabilized by artificial gravity, or deploy self-repairing drones that ride the disk's currents like mechanical plankton. And that raises a provocative question. Have we already glimpsed these megastructures without realizing it? Some supermassive black holes flare with irregular brightness, their emissions defying standard astrophysical models. Others seem too quiet, as if something is intercepting their energy output. It's tempting to dismiss these as quirks of nature, but the universe rarely wastes such colossal forces. If black holes are the ultimate engines of destruction, perhaps someone out there has learned to make them tools instead. The evidence might not be in what we see, but in what we can't explain, the gaps where the cosmos doesn't behave quite the way it should. Matrioshka Brains take the concept of Dyson swarms into the realm of pure computation structures so vast and intricate they don't just harvest a star's energy, but transform it into raw processing power. Imagine a series of nested shells, each one radiating outward like the layers of an onion, built around a star not to capture sunlight for electricity, but to fuel the ultimate supercomputer. The innermost layer absorbs the star's intense radiation, using it for high-temperature calculations. Waste heat from that layer then powers the next shell out, optimized for cooler computations, and so on, cascading energy through dozens or even hundreds of tiers until every photon is wrung dry of usefulness. The result, a computational leviathan capable of simulations on scales we can't fathom, running entire virtual universes, modeling quantum physics in real time, or perhaps even hosting the digitized consciousness of a civilization that long ago left biological bodies behind. But from across the galaxy, how would we recognize such a structure? The answer lies in its light signature. Unlike a Dyson swarm built for energy collection, a Matrioshka brain wouldn't just dim a star unevenly, it would flicker in rhythmic, nested patterns as each layer processes and re-emits heat. Picture a star whose brightness pulses like a heartbeat, not in the regular throbs of a variable star, but in complex, overlapping waves. Some wavelengths might vanish entirely as they're absorbed for computation, while others flare unexpectedly when waste heat spills into space. Telescopes trained on such a star wouldn't just see darkness, they'd detect a symphony of thermal emissions, a fingerprint of artificial thermodynamics at work. The sheer scale of these computations defies imagination. A single Matrioshka brain could perform more calculations in 1 second than all the computers in human history combined. What would a civilization do with that kind of power? The possibilities spiral into science fiction, simulating alternate realities, cracking the fundamental laws of physics, or even creating ancestor simulations so precise they're indistinguishable from the original universe. Some theorists suggest these structures might be the end game of intelligence itself, not expansion outward, but implosion into a self-contained digital cosmos. Yet the eeriest thought isn't what these brains would compute, but how silent they'd be. A civilization inside a Matrioshka brain might have no interest in broadcasting signals into space. Why communicate with the outside universe when you've built your own? This could explain one of the Fermi Paradox's darkest twists, that advanced life isn't missing. It's too busy living inside star-sized supercomputers to notice us. The search for these cosmic computers is already underway. Astronomers have identified stars with bizarre, repeating dimming patterns that resist natural explanations. One candidate, V1332 in the constellation Cygnus, dims in fractal-like waves almost as if something is processing starlight in cascading layers. Of course, dust clouds or other natural phenomena could mimic these signals, but if we ever confirm a Matrioshka Brains' existence, it would mean we've stumbled not just upon alien life, but upon a civilization that has transcended physical limits entirely, turning its sun into the ultimate thinking machine. And that raises a haunting question. If stars can become computers, what happens when they finish their calculations? Imagine a Dyson sphere so advanced, so precisely engineered, that it doesn't just swallow a star's light, it curates it. This is the tantalizing concept of a transparent Dyson sphere, a megastructure designed to filter starlight rather than block it entirely. Instead of a solid shell or a swarm of opaque panels, picture vast arrays of ultra-thin, wavelength-selective materials, like cosmic stained glass floating in orbit around a star. These wouldn't just absorb energy, they'd let certain colors of light pass through while capturing others, leaving behind a spectral fingerprint unlike anything in nature. From a distance, such a star wouldn't vanish, it would transform. Its light spectrum might show sudden, unnatural gaps where specific wavelengths have been siphoned off for energy. Hydrogen alpha lines, crucial for astrophysicists studying star formation, could appear clipped or distorted. Infrared emissions might spike where waste heat leaks through gaps in the collectors, while visible light dims in irregular, artificial-looking bands. It's the difference between a star obscured by dust which dims evenly across all wavelengths and one that's been selectively edited, as if some cosmic engineer tuned its output like a dial. The real brilliance of this design lies in its efficiency. A civilization building a transparent Dyson sphere wouldn't just be after raw power, they'd be optimizing it. By filtering out only the most useful wavelengths for their technology, they could leave the rest of the star's light to sustain photosynthesis on orbiting habitats or even for interstellar signaling. Imagine a star that glows slightly too blue because its redder wavelengths are being harvested, or one that pulses rhythmically as collectors adjust their filtering patterns to match energy demand. These wouldn't be chaotic anomalies, they'd be deliberate, engineered signatures, and here's where it gets even more intriguing. We might have already spotted candidates. Astronomers have catalogued stars with bizarre spectral lines that resist conventional explanations. Take HD 139639, a star whose light spectrum shows abrupt, knife-edge cutoffs in certain ultraviolet bands, as if something is selectively absorbing that energy. Natural processes like circumstellar gas clouds can't explain the precision of these dips, but a transparent Dyson sphere, that fits, yet the implications go beyond mere detection. If such structures exist, they'd represent a level of technological sophistication beyond even classic Dyson swarms. This isn't just about capturing sunlight, it's about refining it, turning a star into a precision instrument. The materials science alone boggles the mind. Think of films just atoms thick, capable of withstanding stellar winds while filtering light with quantum-level accuracy. A civilization that builds these isn't just solving an energy problem, they're mastering the very physics of light itself. And that raises a profound question. Could transparent Dyson spheres be hiding in plain sight? Stars we've dismissed as odd but natural might be anything but. Their spectral quirks could be the equivalent of finding a power cord plugged into a distant sun, evidence that someone out there isn't just using starlight but redesigning it. As telescopes grow more sensitive, these subtle fingerprints might be the key to finding not just alien life, but alien artisans, engineers sculpting light across the galaxy. Science fiction has often been the first to dream of alien megastructures, shaping our cultural imagination long before astronomers began seriously searching for them. Arthur C. Clarke's haunting short story, The Star, offers one of the most poignant examples, a tale where priests discover the remnants of an advanced civilization that perished when their star went supernova. The twist: that star was the biblical Star of Bethlehem, its light heralding both a celestial miracle and a cosmic tragedy. Clarke's brilliance lies in how he intertwines the awe of megastructures with profound existential questions, forcing readers to grapple with the idea that the universe might be indifferent to even its most brilliant architects. But Clarke wasn't alone in weaving megastructures into fiction. Larry Niven's Ringworld introduced a staggering artificial band encircling a star, its scale so vast that Earth would be a mere speck on its surface. Then there's Star Trek's Dyson Spheres, Halo's titular ringworlds, and the mysterious alien constructs in Rendezvous with Rama. These stories do more than entertain. They've shaped how scientists and the public alike conceptualize what might be possible. When Freeman Dyson first proposed his famous sphere in the 1960s, he openly credited science fiction for inspiring the idea, proving that imagination often leaps ahead of theory. What makes these fictional portrayals so compelling is their blend of grandeur and plausibility. A Dyson sphere isn't just a plot device, it's a thought experiment made tangible, inviting us to ask pragmatic questions. How would materials withstand stellar radiation? What would the gravitational stresses be on such a structure? Fiction doesn't just hand-wave these concerns. The best stories wrestle with them, creating blueprints that scientists can refine. The Star's doomed civilization, for instance, mirrors real-world debates about the longevity of technological cultures. If we built a megastructure, could we outlive it? Or would it become our tomb? Public fascination with these ideas isn't accidental. Megastructures tap into something primal, the desire to find meaning in the cosmos, to believe that intelligence can reshape the universe on a godlike scale. When Tabby's star dimmed erratically, it wasn't just astronomers who took notice. Headlines blared about possible alien megastructures, and the public latched onto the mystery with fervor. That excitement isn't just about aliens, it's about the allure of artifacts so vast they defy human-scale comprehension. Yet fiction also warns us of the dangers of projection. Not every unexplained stellar flicker is a Dyson sphere, just as not every strange radio signal is a distress call. The line between inspiration and overreach is thin. But that's the power of these stories. They don't just ask what if. They ask how, why, and at what cost, questions that science is only now beginning to approach with data instead of dreams. As we scan the skies for real-life megastructures, we're unwittingly stepping into the narrative science fiction has been crafting for decades, testing whether the universe is as wild as our stories suggest. KIC 8462852, better known as Tabby's star, isn't just another twinkle in the cosmos. It's one of the most baffling objects astronomers have ever observed. First flagged by citizen scientists in the Kepler mission's data, this seemingly ordinary star, located roughly 1,400 light-years away in the constellation Cygnus, behaves like nothing else in the known universe. Its light doesn't dip in the predictable, symmetrical way a planet would cause. Instead, it dims erratically, sometimes by as much as 22%, in jagged, irregular patterns that last for days or even weeks. At times, the star's brightness drops in sudden plunges, as if something colossal and misshapen is passing in front of it. Other times, it fades gradually over years, like a light bulb on a dying circuit. These anomalies sparked immediate speculation. Could this be the signature of an alien megastructure, a Dyson swarm under construction? The numbers alone defy natural explanations. A Jupiter-sized planet transiting Tabby's star would block less than 1% of its light. Even a swarm of comets, one of the leading natural hypotheses, would need to be impossibly dense to account for the observed dimming. Imagine a cloud of comets so vast it could eclipse a fifth of a star's brilliance. That's not just unusual, it's unprecedented in astronomical records. Yet when researchers trained radio telescopes on Tabby's star, listening for artificial signals, they heard only silence. No pulses, no broadcast, just the quiet hum of a star doing something inexplicable. Dust clouds offer another plausible explanation. In 2017, follow-up observations found that the star's dimming was wavelength-dependent, meaning shorter wavelengths of light were blocked more than longer ones. That's a classic fingerprint of fine dust, not solid megastructures. But here's the catch: dust shouldn't linger for long around a star like this. Radiation pressure should blow it away within years, yet Tabby's star has shown prolonged dimming for over a century, based on historical photographic plates. If it's dust, it's being replenished constantly by some unseen mechanism, perhaps a shattered planet or a colliding asteroid family. Then there's the star's own behavior to consider. Some researchers argue that Tabby's star might be consuming a planet, its gravity tearing apart a world and creating irregular debris fields that occult its light. Others suggest internal stellar magnetism, with sunspots 100 times larger than anything in our solar system causing the dimming. But none of these theories fully explain the star's full repertoire of oddities. The truth might lie in a combination of factors, a cosmic perfect storm of rare phenomena conspiring to mimic the shadows of something artificial. What makes Tabby's star so electrifying isn't just the mystery itself. It's what the debate reveals about how science grapples with the unknown. When faced with something inexplicable, researchers first exhaust every possible natural explanation, no matter how improbable, before considering more exotic possibilities. That's the essence of the scientific method, but it's also why Tabby's star remains an open question. Not because aliens are the most likely answer, but because we haven't yet found a natural one that fits all the evidence. Every new observation peels back another layer, revealing not just the secrets of a single star, but the boundaries of our understanding. Whether it's dust, debris, or something beyond our current physics, Tabby's star has already taught us one invaluable lesson. The universe is far stranger than we imagined, and that's what makes the search so thrilling. While Tabby's star remains the most famous cosmic enigma, it's far from the only stellar oddity that sparked speculation about alien megastructures. Take Epoch 204278916. A young star in the Scorpius-Centaurus association whose light curve left astronomers utterly stunned. Unlike the erratic dips of Tabby's star, Epoch 204278916 dimmed by a staggering 65%, then stayed that way for 25 straight days. That's not just unusual, it's almost unimaginable in natural terms. For comparison, even a Jupiter-sized planet would block less than 1% of a sun-like star's light. To obscure nearly 2/3 of a star's glow, you'd need something truly colossal, or something deliberately designed to do so. Theories about what's blocking Epoch 204278916 range from the extraordinary to the outright bewildering. One leading hypothesis suggests a massive, warped protoplanetary disk, a swirling ring of gas and dust left over from the star's formation, might be tilting at just the right angle to eclipse the star from our vantage point. But here's the catch: disks like that usually belong to much younger stars, and Epoch 204278916 doesn't fit that profile. Another possibility, a family of comets hundreds of times more numerous than anything in our solar system, could be passing in front of the star in a tight-knit swarm. Yet even that struggles to explain the sheer depth and duration of the dimming. What makes Epoch 204278916 especially tantalizing is the shape of its light curve. Natural eclipses like those caused by planets or dust tend to have smooth, symmetrical dips, but this star's dimming was jagged, almost stair-stepped, as if whatever was passing in front of it had complex geometry. That's the kind of signal you'd expect from an artificial structure with uneven surfaces, like a partially completed Dyson swarm or a fleet of enormous solar collectors in chaotic orbits. Of course, extraordinary claims require extraordinary evidence, and most astronomers lean toward natural, if rare, explanations. But the mere fact that megastructures are even part of the conversation shows just how bizarre this star truly is. Then there's V1332 Cygni, another star that defies easy categorization. Unlike Tabby's star or Epoch 204278916, its dimming isn't sporadic. It follows a precise, repeating pattern, fading and brightening like clockwork every 750 days. But here's the twist: the depth of those dips varies wildly, sometimes dropping by just a few percent, other times plunging by nearly 20%. That inconsistency rules out simple planetary transits. Instead, researchers have proposed an equally mind-bending natural explanation: a binary star system where one star is surrounded by a vast, misshapen dust cloud. As the two stars orbit each other, this cloud passes in front of the brighter star, creating those irregular eclipses. Yet even this theory has holes. Dust clouds should scatter starlight predictably, but V1332 Cygni's light curve shows abrupt, almost artificial-looking cutoffs. Could this be the signature of a megastructure in motion, something like a rotating Dyson ring, with sections that intermittently block the star's light as they turn? It's a tantalizing thought, especially when paired with the star's infrared excess, a telltale glow that hints at warm debris, perhaps even waste heat from energy collection. The search for these cosmic anomalies isn't just about hunting aliens. Every unexplained dimming event forces us to expand our understanding of stellar physics, pushing the boundaries of what we thought possible. Whether it's Epoch 204278916's jaw-dropping eclipse or V1332 Cygni's rhythmic flickers, these stars are cosmic puzzles, each one a reminder that the universe is far stranger and far more inventive than our theories can yet explain. And that's the real magic of the hunt. Even if we never find definitive proof of megastructures, the mysteries we uncover along the way are rewriting astronomy itself. When we search for life beyond Earth, we're really hunting for two kinds of clues: biosignatures and technosignatures. Biosignatures are the chemical fingerprints of life itself, like oxygen in an exoplanet's atmosphere or methane spikes that hint at biological activity. They answer the question, does anything live here? Technosignatures, on the other hand, are the echoes of intelligence, radio signals, industrial pollutants, or in this case, the shadow of a megastructure blocking starlight. They ask something far more provocative: is anyone building here? The difference between these two types of signals isn't just academic, it's cosmic. A biosignature might reveal microbes thriving in an alien ocean, but a technosignature could point to a civilization capable of rearranging solar systems. Take light blocking, for example. A natural phenomenon like a planet transiting its star creates a predictable, rhythmic dip in brightness. But when something blocks light unevenly at scales that defy natural explanations, that's when technosignature hunters lean in. It's the difference between finding a tree in a forest and finding a skyscraper. One suggests life, the other suggests purpose, yet not all technosignatures are deliberate. A Dyson swarm under construction might block starlight incidentally, simply as a byproduct of its energy harvesting. Other structures, like a Shkadov thruster nudging a star across the galaxy, could leave detectable shadows without their builders ever intending to signal their presence. On the flip side, some technosignatures might be intentional broadcasts. Imagine a civilization using mirrored megastructures to flash coded messages across interstellar distances, turning their entire star into a beacon. Biosignatures, by comparison, are quieter. They don't require intelligence, just chemistry. A distant planet's atmosphere might betray the presence of algae or extremophiles through subtle spectral lines, but it won't show the jagged, engineered asymmetry of a megastructure's shadow. That's why technosignatures like light blocking are so electrifying. They don't just hint at life, they scream civilization, and not just any civilization, but one that's reached a scale where it can bend starlight to its will. The challenge lies in telling them apart. A star's odd dimming could be caused by a swarm of comets, a natural biosignature of sorts, indicating a bustling solar system, or a half-built Dyson sphere, a technosignature shouting into the void. That's where context matters. Is the star young, prone to violent flares that might shred artificial constructs? Or is it stable, its light curves too precise for natural chaos? The more we study these anomalies, the better we get at reading the universe's cryptic signatures, whether they're written in chemistry or steel. In the end, biosignatures and technosignatures represent two very different dreams. One promises companionship in the cosmos, the thrill of knowing we're not alone. The other promises conversation, the dizzying possibility that somewhere, someone is not just living among the stars but changing them. And if we ever catch the shadow of a megastructure drifting across a distant sun, it won't just answer Fermi's paradox, it'll rewrite our place in the universe, from solitary observers to students of a galaxy far wiser than we imagined. The Kardashev scale isn't just a way to measure energy use, it's a roadmap of civilizations, from planet-bound beginners to galaxy-spanning architects. Proposed by Soviet astronomer Nikolai Kardashev in 1964, this scale categorizes civilizations based on how they harness power, with each leap forward rewriting the rules of what's possible. A Type I civilization, like one we might achieve in the next few centuries, masters all the energy resources of its home planet, tapping geothermal heat, controlling weather, and maybe even bending sunlight to its will. But a Type Roman II civilization, that's where megastructures come into play. These are cultures that don't just live on a world, they command the star itself, building Dyson swarms or Shkadov Thrusters to capture and manipulate stellar energy on scales that make our biggest power grids look like campfires. Think about what that leap means. For humanity to reach Type Roman II, we wouldn't just need better solar panels or fusion reactors. We'd need to fundamentally reshape our relationship with matter, energy, and even time. Constructing a Dyson swarm, for instance, would require mining entire planets for materials, deploying self-replicating robots to build in the void, and mastering orbital mechanics with precision we can't yet fathom. And that's just the engineering. The social and political shifts would be just as staggering. Imagine a society where energy is so abundant that scarcity becomes obsolete, where the concept of running out vanishes from the language. But here's the most mind-bending part. If we ever detect a megastructure around a distant star, it won't just tell us aliens exist. It'll reveal they've crossed this evolutionary threshold, transitioning from a species that exploits its planet to one that engineers its solar system. That's the real significance of the Kardashev scale. It's not just about power output, it's about intent. A Type Roman II civilization isn't just surviving, it's optimizing, turning chaos into order on a cosmic scale. The very act of building a megastructure signals a culture thinking in millennia, not quarterly reports. Yet the scale has its limits. Kardashev originally framed it as a linear progression, Type I to Type Roman II to Type Roman III, the last being a civilization that harnesses the energy of an entire galaxy. But what if some cultures skip steps? A species might leapfrog planetary energy altogether, using nanotechnology to build Dyson swarms before they've even unified their world's politics. Or perhaps they'll reject expansion entirely, collapsing into virtual realities powered by a single star. The scale assumes growth follows a predictable path, but the universe loves surprises. That's why megastructures are such tantalizing clues. They're not just feats of engineering, they're cultural artifacts, revealing how a civilization sees its place in the cosmos. A Dyson sphere suggests a species obsessed with growth. A Matrioshka brain hints at one that values computation over exploration, and a star-shrouding cloak. That might belong to a culture that's learned the hard way that silence is survival. Each megastructure is a message in steel and light, whispering across the light years not just "we are here," but "this is what we became." So when we scan the stars for these cosmic monuments, we're not just hunting for aliens. We're looking for our own possible futures, blueprints of what humanity might one day build, or what might lie in wait for us out there in the dark. Detecting alien megastructures isn't as simple as pointing a telescope at the sky and waiting for a glint of metal. It's a cosmic game of hide and seek where the clues we're hunting, subtle dips in starlight, unusual heat signatures, are often drowned out by the universe's natural chaos. Take transit photometry, the workhorse of modern exoplanet searches. This method watches for the telltale dimming of a star as planets pass in front of it, like a moth flitting across a porch light. But when that dimming isn't clean and symmetrical, when it's jagged or irregular, that's when astronomers' curiosity ignites. The Kepler Space Telescope revolutionized this approach, scanning hundreds of thousands of stars for these shadowy anomalies. Most turned out to be planets or dust clouds, but a handful, like Tabby's star-defied explanation, their light curves too erratic to fit any natural model. Yet photometry alone can't confirm a megastructure. That's where infrared excess comes in, the thermal fingerprint of waste heat. Every energy harvesting system, no matter how advanced, must obey the laws of thermodynamics. A Dyson swarm absorbing sunlight would re-radiate that energy as infrared glow, creating a star that appears unusually dim in visible light but oddly bright in longer wavelengths. Telescopes like NAS, a wide-field infrared survey explorer, have scanned the skies for exactly this mismatch, flagging stars that glow too warmly for their size. Some candidates, like the bizarre object TUSE 4144244351, show exactly this paradox: visible light dimmed by something, while infrared emissions spike. But here's the catch: cosmic dust can mimic this effect almost perfectly. A star shrouded in debris from planetary collisions might look identical to one wrapped in solar panels, at least from hundreds of light years away. Distance itself is another formidable hurdle. Even our most powerful telescopes struggle to resolve details beyond a few pixels when observing distant stars. A megastructure around Proxima Centauri, our nearest stellar neighbor, would still appear as little more than a flicker. That's why projects like Breakthrough Listen focus not just on light, but on other technosignatures, radio transmissions, laser pulses, even gravitational wave patterns that might betray artificial origins. The idea isn't just to find megastructures, but to listen for the civilizations that built them. But nature loves to deceive. Take Boyajian's star again. Its dimming initially seemed so unnatural that speculation about alien engineering ran wild. Later observations, though, pointed to fine dust as the likely culprit. Similarly, pulsars, rapidly spinning neutron stars, were briefly mistaken for extraterrestrial beacons when first discovered in 1967, their clockwork radio pulses eerily precise. The lesson: the universe is brimming with phenomena that can masquerade as intelligence, from stellar flares to rogue comets to interstellar gas clouds. That's why SETI researchers embrace a mantra: extraordinary claims require extraordinary evidence. Before declaring a dimming star proof of aliens, they exhaust every possible natural explanation. It's tedious work sifting through cosmic static for a signal that might not even exist, but the tools are improving. Next-generation telescopes like the Vera C. Rubin Observatory will monitor billions of stars with unprecedented precision, while space-based infrared observatories like the James Webb Space Telescope can dissect the thermal fingerprints of distant suns in exquisite detail. Combine these with AI-driven data analysis, and the odds of spotting something truly anomalous improve dramatically. The real breakthrough won't come from a single observation, but from a pattern, a star whose behavior defies not just one natural explanation, but all of them. Until then, the search continues, a delicate dance between skepticism and wonder, where every odd flicker of light could be the signature of something unimaginable, or just another quirk of a universe that's always one step ahead of our theories. The hunt for alien megastructures isn't just a job for astronomers, it's a task for algorithms. With telescopes like the Vera Rubin Observatory set to scan the sky every few nights, generating petabytes of data on billions of stars, the old way of searching, eyeballing light curves one by one isn't just outdated, it's impossible. That's where artificial intelligence steps in, not as a replacement for human curiosity, but as a force multiplier, sifting through cosmic noise to find the needles in a haystack the size of the galaxy. Machine learning models trained on known stellar behaviors can flag anomalies in real time, spotting patterns too subtle or complex for even the most seasoned researchers to catch. Imagine sorting through 1 million flickering light bulbs to find one that dims just a little differently. AI doesn't just make that feasible, it makes it routine. These algorithms don't work on hunches. They're fed vast catalogs of natural stellar phenomena, pulsating variable stars, eclipsing binaries, planetary transits until they learn the rhythm of the cosmos. Then they go hunting for the outliers, the stars that break the rules. Projects like SETI Laser Fermi or the Breakthrough Listen initiative already use similar techniques to scan radio signals, but the Rubin Observatory's Legacy Survey of Space and Time, or LSST, will take it further. Over a decade, it'll image the entire southern sky in unprecedented detail, creating a movie of the universe where every frame contains 10 million galaxies and stars. Without AI, that deluge of data would drown any hope of finding megastructures. With it, we've got a shot. The real power lies in the subtlety of these tools. Traditional searches might look for the obvious, a star that's gone dark, but machine learning can detect the fingerprints of partial Dyson swarms or Shkadov Thrusters in ways humans might miss. Maybe it's a star whose dimming pattern doesn't quite match dust clouds, or one whose infrared glow is a fraction too warm for its age. These aren't smoking guns, they're whispers, and AI excels at listening. Yet for all their precision, these systems aren't infallible. They're only as good as the data they're trained on, and the universe loves to surprise us. When an AI flagged Boyajian's star as anomalous, it wasn't wrong, but the truth turned out to be stranger than any algorithm could anticipate. That's why the best searches pair machine efficiency with human intuition, letting AI narrow the field so scientists can probe deeper. The future of this collaboration is already taking shape. Neural networks are learning to simulate hypothetical megastructures, predicting how their light curves might look from light years away. Other models are being trained to distinguish between natural cosmic oddities like rogue planets with rings of debris and the signatures of something engineered. It's a cosmic detective story where the clues are photons and the suspects could rewrite history. But here's the beautiful paradox: the more we automate the search, the more human it becomes. AI handles the drudgery, freeing researchers to ask bigger questions. What if the anomaly isn't a Dyson sphere, but something we haven't even imagined yet? What if the real breakthrough comes not from finding what we're looking for, but from discovering how much we've overlooked? In that tension between the machine's precision and the scientist's wonder lies the next chapter of the hunt for alien megastructures. Einstein's theory of relativity gave us an astonishing prediction: mass bends spacetime, warping the very fabric of the universe around it. Stars, galaxies, even black holes act like cosmic lenses, distorting and magnifying the light of objects behind them in a phenomenon called gravitational lensing. Now imagine something even more deliberate, a megastructure so massive, so precisely engineered that it doesn't just block starlight, it bends it into unnatural patterns. Unlike natural lenses caused by stars or black holes, An artificial gravitational lens would carry signatures of intent asymmetries, precise focal points, or even repeating distortions that resemble the optical effects of a gigantic engineered lens. Consider the possibilities. A civilization capable of manipulating space-time on this scale might build a megastructure designed not just to collect energy but to focus it. Picture a colossal ring of hyperdense material orbiting a star, creating a lens so powerful it could beam energy across interstellar distances, or even transmit signals by warping light into focused pulses. From our vantage point, such a structure wouldn't just dim the star, it would split its light into multiple images, create rings or arcs of distorted background galaxies, or even produce recurring flashes as the lens rotates. These wouldn't be the chaotic warping of a black hole's gravity. They'd be precise, repeating distortions like the difference between a funhouse mirror and a telescope. The hunt for these anomalies is already underway. Astronomers using telescopes like Hubble and the upcoming Nancy Grace Roman Space Telescope study gravitational lensing to map dark matter and distant galaxies. But buried in that data could be something far stranger, a lens that's too perfect, too regular, or positioned in ways that defy natural celestial mechanics. Take the case of quasars lensed by foreground galaxies. Their multiple images follow predictable patterns based on the galaxy's mass distribution. But if a lens produced 4 identical, equally spaced copies of a background star with no galaxy in sight, that would raise eyebrows. There's a darker twist to this idea. Some theorists suggest advanced civilizations might use gravitational lenses as shields, not just bending light but weaponizing it. A sufficiently massive lens could focus a star's energy into a beam intense enough to vaporize planets or propel interstellar ships at relativistic speeds. The same megastructure that powers a civilization could also defend it, turning an entire solar system into a fortress. Yet the most tantalizing prospect isn't destruction, it's communication. A megastructure designed as a gravitational lens could function as the universe's ultimate telescope, resolving details on distant planets with impossible clarity. Or it might serve as a beacon, deliberately warping light in rhythmic patterns to signal other civilizations. The distortions would outlast radio waves, persisting across millennia as a monument to intelligence written not in stone or steel, but in the curvature of spacetime itself. Gravitational lensing offers a silent advantage in the search for alien megastructures. It doesn't rely on catching a civilization in the act. Unlike radio signals or fleeting construction shadows, a lens's imprint lingers. Even if the builders are long gone, their architecture would still bend the light of distant stars, etching their presence into the cosmos. That's the haunting beauty of this search. We might not find engineers. We might find their monuments. Among the countless stars in our galaxy, some might be flashing messages not with radio waves, but with the shadows of megastructures. The idea that advanced civilizations could use entire stellar systems as communication beacons isn't just science fiction. It's grounded in the SETI beacon hypothesis, which suggests that deliberate, detectable signals might be embedded in the very light of distant suns. Imagine a Dyson swarm not just harvesting energy, but pulsing rhythmically, dimming its star in precise, repeating patterns. A cosmic Morse code broadcast across light years. These wouldn't be random flickers, but mathematical sequences, prime numbers, Fibonacci spirals, or even binary pulses encoding fundamental constants like pi or the hydrogen line frequency. Such signals would be unmistakably artificial, a deliberate scream into the void saying, "We are here." This concept isn't new. In 1974, we aimed our own message at the stars, the Arecibo broadcast, a binary encoded signal describing Earth's biology and location. But compared to a star-sized beacon, Arecibo was a whisper. A megastructure signaling with starlight could outshine entire civilizations, visible to any species with basic astronomy. Take Boyajian's star again. Its erratic dimming initially sparked speculation about alien engineering. While natural explanations now seem more likely, its irregular patterns show how even unintentional light blocking grabs attention. A purposeful signal, though, would be far more structured, like the difference between a campfire's flicker and a lighthouse's steady flash. The beauty of stellar beacons lies in their endurance. Radio signals fade over interstellar distances, distorted by cosmic dust and plasma. But a star's light travels cleanly across millennia, its brightness variations preserved like etchings in spacetime. A civilization could encode entire libraries in these pulses, broadcasting not just hello, but complex information, blueprints, histories, or warnings. Some theorists even propose that advanced cultures might synchronize multiple stars, creating a galaxy-wide network of linked beacons, their combined patterns forming a message too vast for any single world to decipher alone. Yet the challenge is recognizing these signals amid nature's noise. Pulsars, for instance, emit clockwork radio bursts so precise they were initially dubbed LGM for little green men. Even now, astronomers must distinguish between natural stellar variability and potential technosignatures. That's where machine learning comes in. Algorithms trained to spot anomalies in light curves, flagging stars whose dimming patterns resemble intentional sequences rather than random fluctuations. Projects like SETI laser Fermi are already scanning for pulsed laser signals, but the same logic applies to megastructures. A star dimming in prime-numbered intervals or tracing the digits of pi in its brightness dips would stand out like a flare in the cosmic night. There's a haunting elegance to this idea that the universe's most advanced civilizations might not broadcast on radio frequencies, but in the language of starlight itself. They wouldn't need to build transmitters, they'd repurpose their energy infrastructure into a beacon, turning necessity into communication. And if we ever decode such a signal, it won't just reveal that we're not alone. It'll show that somewhere, someone looked up at the sky and chose to speak in the only vocabulary that spans the cosmos: light, time, and the patient pulse of stars. Discovering an alien megastructure wouldn't just rewrite astronomy, it would force humanity to confront ethical dilemmas we've never faced before. Consider the sheer scale of a civilization capable of engineering stars. They wouldn't just be ahead of us technologically, they'd operate on timescales and priorities beyond our comprehension. If we detected a Dyson swarm or a Shkadov thruster, the immediate question wouldn't just be, what is it, but should we respond? Broadcasting our presence to a species that might see us as insignificant, or worse, as a resource, could be reckless. History on Earth shows what happens when advanced cultures encounter less technologically developed ones, and the results are rarely equitable. The ethical weight of first contact wouldn't just fall on scientists, it would demand global consensus, a unified voice for humanity in a conversation where a single misstep could echo across millennia. Yet silence carries its own risks. If an advanced civilization is deliberately signaling with megastructures pulsing starlight in mathematical patterns, for instance, ignoring them might be seen as hostility or disinterest. Philosophers have long debated the zoo hypothesis, the idea that extraterrestrial societies might intentionally avoid contact to let us develop undisturbed. But what if their megastructures are the contact, a passive invitation to join a galactic dialogue? The very act of observation could be the first step in a relationship we don't yet understand, and refusing to engage might isolate us from a cosmic community we're only beginning to perceive. The philosophical implications run even deeper. Confirming the existence of star-building civilizations would shatter our anthropocentric view of intelligence. Human history, with its wars, art, and empires, might represent just the first flickers of consciousness in a universe where other minds have already harnessed the energy of suns. It's humbling and unsettling to realize we could be the youngest species at the table, struggling to comprehend technologies that border on magic. Some thinkers argue this realization would unite humanity, dissolving terrestrial conflicts in the face of a shared cosmic perspective. Others fear it could trigger existential despair, a collective crisis of purpose when confronted with civilizations that have outpaced us by millions of years. Then there's the question of their motives. A culture that builds megastructures might not even recognize us as equals or at all. Their priorities could be as alien as their technology, focused on projects we can't fathom. Would they see Earth as a curiosity, a threat, or irrelevant noise in their grand designs? The uncertainty itself is a frontier, forcing us to grapple with humanity's place in a universe that might be indifferent, benevolent, or so vastly complex that our categories of thought don't apply. Perhaps the most profound shift would be in how we view our future. If megastructures exist, they prove that intelligence can survive its technological adolescence, that civilizations don't inevitably destroy themselves with the tools of their own making. That's a beacon of hope, but they also present a mirror. Are we destined to become builders of stars, or is our path different? The answers wouldn't just come from telescopes, but from the choices we make next, whether to reach out, to listen, or to quietly grow until we too can shape the light of suns. Whatever we decide, the stars will keep their secrets a little longer. The universe is full of cosmic illusions, phenomena so bizarre they can trick even the most sophisticated telescopes into seeing megastructures where none exist. Take rogue planets, for instance. These are worlds untethered to any star, drifting through the void like dark nomads. When one passes in front of a distant sun, its gravitational field can bend and magnify the star's light in a process called microlensing. From our vantage point, the star might appear to brighten and dim asymmetrically, mimicking the erratic flicker of a partially constructed Dyson swarm. Even more confounding, some rogue planets could be sheathed in thick rings of debris. Think Saturn's rings scaled up 1,000-fold. As they transit, these jagged, uneven rings could block starlight in irregular patterns, creating light curves that look eerily artificial. The key giveaway: microlensing events are one-time occurrences, whereas megastructures would leave repeating, engineered shadows. Then there's the puzzle of circumstellar disks, swirling maelstroms of gas and dust around young stars. These disks aren't just flat, uniform sheets, they're dynamic, warped, and pockmarked with gaps where nascent planets are forming. When viewed edge-on, a misaligned disk can eclipse its star in complex ways. Some, like the one around J1407, dim their stars by up to 95%, with dips lasting weeks or months. The uneven absorption of starlight by dust grains of varying sizes can produce jagged, stair-step dimming that mirrors the signature of a megastructure under construction. The smoking gun: these systems often glow brightly in infrared, their heat revealing the presence of dust, something a solid Dyson swarm would lack. Hypergiant stars add another layer of cosmic deception. These colossal, unstable behemoths like Eta Carinii or Vui Canis Majoris pulsate erratically, their surfaces bubbling with convection cells the size of solar systems. They might shed entire planetary masses of material in sporadic outbursts, eclipsing themselves with shrouds of ejected gas. In the 1980s, the star Arcorini Borealis puzzled astronomers by dimming unpredictably, sometimes vanishing for years. Later, we learned its atmosphere is so carbon-rich that it periodically forms soot-like clouds, blocking its own light. To an observer searching for technosignatures, this could resemble a star being systematically shrouded, but the truth is far more violent and natural. Even the universe's most extreme events can masquerade as engineering. When a star is torn apart by a supermassive black hole, a tidal disruption event, the resulting debris forms a glowing, clumpy disk. As this material spirals inward, it can eclipse the central black hole in chaotic bursts, mimicking the flicker of a megastructure's shadow. Similarly, colliding neutron stars produce kilonovae, whose light curves include abrupt, asymmetric dips as heavy elements like gold and platinum condense in their ejecta, filtering specific wavelengths. These aren't just exotic oddities, they're cosmic red herrings, nature's way of testing our assumptions. the lesson here isn't just caution, it's humility. The universe is a master of disguise, capable of crafting illusions that challenge our search for intelligence. Yet every false positive sharpens our tools, teaching us to distinguish the fingerprints of engineering from the brushstrokes of natural chaos. As the hunt for megastructures continues, the greatest discovery might not be aliens at all, but a deeper understanding of the cosmos' boundless creativity. The next generation of telescopes won't just observe the universe, they'll dissect it with unprecedented precision, peeling back the layers of cosmic mystery to reveal details we can currently only imagine. At the forefront is the James Webb Space Telescope, already rewriting the rules of infrared astronomy with its ability to detect the faintest thermal fingerprints of distant stars. But Webb is just the beginning. Projects like LUVOIR, the Large UV Optical Infrared Surveyor, promise resolutions so sharp they could distinguish the individual components of a Dyson swarm from hundreds of light-years away. Imagine not just detecting a star's dimming, but mapping the silhouette of whatever's blocking it, discerning the jagged edges of solar collectors or the geometric perfection of an artificial ring. These instruments don't just see more, they see differently. Where current telescopes might spot a star dimming unevenly, next-gen tools like the Habitable Worlds Observatory will analyze that dimming across hundreds of wavelengths simultaneously. This isn't just about brightness, it's about composition. A natural dust cloud dims light in predictable spectral patterns, but a megastructure built from unfamiliar alloys or metamaterials might absorb specific wavelengths in ways no natural substance could. Subtle anomalies in starlight, like the absence of certain ultraviolet bands or an unexpected spike in infrared, could betray the presence of materials engineered to harness energy more efficiently than nature ever intended. Then there's the game-changer, temporal resolution. Telescopes like the Vera Rubin Observatory will monitor the entire visible sky every few nights, creating a real-time movie of the cosmos. Imagine catching a star mid-eclipse, watching as something massive and asymmetrical drifts across its face over days or weeks. Previous surveys might have missed such events as one-off anomalies, but Rubin's relentless gaze could capture their full progression, revealing whether these shadows move with the chaotic tumble of natural debris or the precise orbits of something designed. But the true revolution lies in synergy. Combining Webb's infrared sensitivity with LUVOIR razor-sharp optics and Rubin's panoramic coverage creates a detection net no cosmic oddity can escape. A star behaving strangely in one wavelength, cross-reference it against another telescope's data to see if the anomaly holds. A flicker that looks artificial in visible light but matches known dust signatures in infrared. Likely natural, but if the signals contradict, if the star's dimming shows the hallmarks of solid structures in some wavelengths while radiating waste heat in others, that's when the hunt gets serious. The most exciting possibility isn't just finding megastructures, it's understanding them. Future spectrographs could analyze the chemical makeup of distant starlight filtered through potential megastructures, searching for industrial pollutants or exotic elements that hint at technology. Polarimetry might detect the unnatural alignment of reflected light from mirrored surfaces. Even gravitational wave detectors, tuned to the right frequencies, could sense the vibrations of colossal artificial objects shifting in orbit. Yet for all their power, these telescopes will also teach us humility. Every new instrument reveals how much we've misunderstood, how phenomena we once dismissed as noise might hold clues we lack the tools to see. The universe's greatest secrets aren't just hidden in darkness, they're waiting for the right light to reveal them. And with these machines, we're not just turning on that light. We're bending it to our will. Dyson swarms and Matrioshka brains might dominate the conversation, but they're just the beginning of what cosmic engineering could look like. Consider star lifting, a process so audacious it sounds like science fiction, yet obeys the cold logic of physics. imagine a civilization not content with merely harvesting a star's light, but actively mining its very substance. Using powerful magnetic fields or focused lasers, they could strip away layers of stellar plasma, siphoning off hydrogen and helium to fuel fusion reactors or build new worlds. The star wouldn't just dim, it would slowly shrink, its light fading over centuries as its mass is repurposed into orbital habitats or even entirely new stars under artificial control. Unlike the clean shadows of a Dyson sphere, star lifting would leave spectral scars, missing absorption lines where elements have been systematically extracted, turning the star's chemistry into an open ledger of industrial activity. Then there's the concept of fusion inhibitors, megastructures designed not to block light, but to throttle a star's core. Picture vast magnetic coils wrapped around a star like cosmic shackles, damping its nuclear reactions to extend its lifespan or prevent catastrophic flares. The result, a star that burns too steadily, its variability suppressed in ways no natural process could achieve. Astronomers might notice the absence of expected solar cycles or the strange homogeneity of its light output, as if something were fine-tuning the furnace at its heart. Unlike the obvious shadow of a Dyson swarm, these structures would whisper their presence through stellar behavior that defies astrophysical models, a sun that refuses to age or erupt as it should. Some theories push even further into the speculative. Imagine a civilization that doesn't just build around stars but rewires them. Quantum dot swarms, nanoscale crystals tuned to absorb specific wavelengths, could be dispersed in a star's upper atmosphere, filtering its light with atomic precision. The star might appear to shift color over time, its spectrum engineered to optimize energy collection or even transmit information through deliberate spectral lines. Other proposals include stellar engines that don't just move stars, but reshape them using gravitational shearing to flatten a star into a disk, increasing its surface area for energy harvesting, or inducing controlled nova events to expel usable material. The most radical idea of all, turning stars into tools. A sufficiently advanced civilization might modulate a star's output like a dial, pulsing it to power interstellar propulsion lasers or creating resonant frequencies to communicate across galaxies. These wouldn't be passive megastructures, but dynamic instruments playing the cosmos itself like an orchestra. The evidence wouldn't be in what's blocking the light, but in its unnatural rhythms, a stellar heartbeat too precise for nature to mimic. What unites these concepts is their shared audacity. They're not just constructions, they're reimaginations of stars themselves, treating these cosmic furnaces not as immutable facts of nature, but as raw material for engineering on a scale that dwarfs planets. And that's the real challenge in searching for them. We're not just looking for objects in space, we're looking for intelligence that has rewritten the rules of astrophysics, not with magic but with mastery. When news first broke about Tabby's star and its bizarre dimming patterns, the reaction was electric but not unanimous. Scientists split into two camps almost immediately. Some, like Penn State astronomer Jason Wright, openly entertained the possibility of alien megastructures, arguing that extraordinary claims deserve rigorous investigation, not automatic dismissal. Others, like SETI Seth Shostak, urged caution, pointing out that the universe is full of natural oddities we don't yet understand. The debate played out in journals, conferences, and unusually for such a niche topic, mainstream headlines. Media outlets seized on the megastructure angle with breathless proclamations like, "Have we found aliens?" splashed across magazines and news feeds. But beneath the hype, a quieter, more consequential conversation was unfolding. How to balance open-minded exploration with the skepticism that keeps science grounded. The tension between these approaches isn't new. History is littered with cosmic mysteries initially mistaken for alien engineering, from pulsars dubbed LGM-1, little green men, to the infamous WOW signal, a radio burst so peculiar it's never been fully explained. Each time, the scientific method acts as a corrective, tempering excitement with evidence. But Tabby's star marked a shift. Instead of dismissing the megastructure hypothesis outright, researchers treated it as a falsifiable claim, testing it against increasingly sophisticated natural explanations. That's progress. A century ago, anomalies were often ignored or shoehorned into existing theories. Today, we're willing to follow the data, even if it leads somewhere unsettling. Public fascination, though, operates on different rules. The idea of alien megastructures taps into something deeper than curiosity. It's a mirror for our hopes and fears about humanity's future. When the Kepler team released data on Tabby's star, citizen scientists flooded online forums with theories, some meticulously researched, others wildly speculative. Crowdfunding campaigns sprang up to secure telescope time for further observations, proving that the hunt for cosmic neighbors isn't just academic. It's a cultural phenomenon, a shared story we tell ourselves about what might be out there. Yet for all the enthusiasm, the media's aliens or bust framing risks distorting the real work of science. Headlines tend to leap from anomaly to extraterrestrials, skipping over the painstaking process of elimination that defines actual research. Take Boyajian's star. After years of study, most astronomers now agree its dimming likely stems from dust, not Dyson swarms. That conclusion isn't a letdown, it's a triumph of careful observation. The universe doesn't owe us aliens, but it does reward patience. What's striking is how the megastructure hypothesis has matured. Once relegated to fringe discussions, it's now a legitimate branch of astrobiology, complete with peer-reviewed frameworks for distinguishing artificial from natural phenomena. Projects like the Galileo project, which aims to systematically study unidentified aerial phenomena, reflect this new openness. The goal isn't to prove aliens exist, but to apply the same rigor to technosignatures that we do to biosignatures. That's the legacy of Tabby's star, not proof of extraterrestrial engineers, but proof that we're finally asking the right questions, with humility, creativity, and a willingness to be wrong. The lesson here isn't just about aliens, it's about how we confront the unknown. Science thrives when it balances bold ideas with merciless scrutiny, when it lets curiosity and skepticism coexist. Whether the next cosmic anomaly turns out to be dust, comets, or something far stranger, the conversation it sparks will be just as valuable as the answer. After all, the universe isn't just a puzzle to solve, it's a mirror, showing us who we are and who we might become. The search for alien megastructures isn't just about finding answers, it's about rediscovering the universe as a place of infinite possibility. Every unexplained dimming star, every flicker of infrared light where none should be, is a reminder that we've only just begun to scratch the surface of what might be out there. Whether these cosmic anomalies turn out to be Dyson swarms, rogue planets, or something beyond our current imagination, the hunt itself has already reshaped how we see the cosmos. No longer just a collection of stars and gas, the galaxy becomes a potential workshop, a canvas where civilizations far older and wiser than ours might have left their mark in steel and starlight. But here's the most thrilling part. We're living in the era where these questions move from science fiction to testable science. Telescopes like JWST and Vera Rubin are turning speculation into data, replacing "what if" with "let's measure." And while we might not find definitive proof tomorrow or even in our lifetimes, the act of looking changes us. It sharpens our tools, refines our theories, and perhaps most importantly, keeps alive that childlike wonder that first made us gaze up at the night sky and dream. So stay curious. The next great cosmic mystery might already be hiding in plain sight, buried in data or flickering in the light of a star no one's paying attention to yet. And who knows, maybe the breakthrough won't come from a lab or a telescope, but from someone like you spotting a pattern everyone else missed. Until then, the universe is full of stories waiting to be told. Maybe they're stories of civilizations that turned stars into engines, or of nature's infinite creativity outshining even our wildest fantasies. Whatever the truth, it's out there, and the journey to find it is half the fun. So drop your favorite theory, your most loved sci-fi megastructure, or just your boldest cosmic dream in the comments. Let's keep the conversation as vast as the cosmos itself. After all, the next chapter of this story isn't just written by scientists, it's written by anyone brave enough to look up and wonder.